Good morning, students. Today's lecture is on simple binomial logistic regression using SPSS. In this lecture, we are using an example where independent variable is continuous. I am Dr. Sandeep Sugadan, Associate Professor in Community Medicine, Quest International University, Malaysia. What is simple binomial logistic regression? Binomial logistic regression, it is referred to as logistic regression, predicts the probability that an observation falls into one of two categories of a dichotomous dependent variable. Dependent variable is dichotomous or binary, based on one independent variable that can be either continuous or categorical. There are many assumptions for doing simple binomial logistic regression. Assumption 1 is that dependent variable should be measured on a dichotomous scale in which categories are mutually exclusive. Assumption 2, there can be one independent variable which can be either continuous or categorical. Because there is only one independent variable, it is known as simple binomial logistic regression. In multiple binomial logistic regression, number of independent variables will be multiple. Assumption 3, there should be independence of observation. That means data is collected using representative sampling method. Okay, now we can go through the steps in SPSS data. First, you have to click on Analyze button, then click on Regression. There are so many options for regression, but you need to select Binary Logistic option because we are doing simple binary logistic regression or simple binomial logistic regression. Okay, then logistic regression dialog box appear. Please select dependent variable. In this case, dependent variable is presence of heart disease. Heart disease will be coded as yes or no, present or absent. Okay, that is a dependent variable. Dependent variable is dichotomous. Then independent variable, you please select age. Age is the independent variable. In this case, age is a continuous variable. Okay, please select age and move to the box covariates. So dependent variable, you select presence of heart disease. Whatever you select should be outcome variable and it should be binary or dichotomous. Independent variable, it's continuous variable. You please select as covariates. Then click options button. Then one box for options appear. So you need to select whatever options required. So we need to select classification plots. It will show how much of the outcome are classified correctly by the regression model. Hosmer, Limshaw, Goodnessoffit, that will show how much good the model is. In this lecture, whenever we are discussing about model, it is a regression model. When we elaborate, it is a regression model for predicting the development of heart disease based on the continuous independent variable, that is age. In this regression model, outcome variable is development of heart disease, which is binary or dichotomous, and independent variable is age. It is continuous. Hosmer, Limshaw, Goodnessoffit checks if the regression model is fit or not. case-wise listing of residuals. So in this case, outliers outside 2 standard deviation. So computer will remove the outliers which are outside 2 standard deviation. Confidence interval of exponential b. Confidence interval for exponential b, we need to select 95%. Exponential b is another name for odds ratio in logistic regression analysis. It is a exponential of regression coefficient. Regression coefficient is b. Exponential of regression coefficient is the odds ratio, equivalent to odds ratio. So when you click on confidence interval for exponential b, computer will calculate 95% confidence interval of odds ratio. And display the result at the last step. So computer will give you the final result. What is the odds ratio at the final result? Then include constant in model. That also you need to click. After that, click continue, then click OK. Okay, then results appear. First table will be model summary. So there are so many statistical values here. As a researcher, we need to focus on one value here, that is Nagelkerk R squared. Nagelkerk R squared, we need to convert it into percentage. Here Nagelkerk R squared value is 0.155. So we need to convert it into percentage, that is 15.5%. So what is the significance of this value, The model which included independent variable age explained 15.5% of the variance in development of heart disease. If Nagelkerk R squared is 15.5%, that means 15.5% of variance in outcome variable. Here 15.5% of variance in development of heart disease can be predicted by the regression model. When we elaborate regression model of adding age as the independent variable. Is it clear? Nagelkerk R squared 0.155 means 15.5% of variance in dependent variable can be predicted by the regression model of adding independent variable of age. Now we can look at Hosmer and Limshaw Goodnessoffit test. Here we need to look for significance value. Here one thing please remember, if significance value or p-value is more than 0.05, model is good. P-value of more than 0.05 means that model which included the independent variable age in predicting the development of heart disease is fit. It's a Goodnessoffit test. Another one, for model fit, another table also there. They use chi-square test, and for model they give a chi-square value, degree of freedom value and significance value. In this omnibus test, model shows significance. That means logistic regression model which included the independent variable age in predicting the development of heart disease was statistically significant. Please keep in mind, for Hosmer and Limshaw Goodnessoffit, you have to check if significant value is more than 0.05. Here in chi-square test, you have to check if model significant value is less than 0.05. Here it is less than 0.05, so model is fit. Model is good. Okay, chi-square value is 11.907, degree of freedom is 1, and significance value for the model is significant, that is less than 0.05. Now we can go for classification table. Classification table is a regression model which included the independent variable age in predicting the development of heart disease correctly classified. Okay, the outcome. Correctly classified outcome means they predicted correctly. Okay. Presence of heart disease was present in 25 plus 10, 35 cases. Presence of heart disease was not there. No heart disease was there in 65 cases. Out of those, how many are predicted correctly? Okay. Correct prediction for heart disease present individuals were 28.6%. Correctly predicted for no heart disease individual was 90.8%. Overall, 69.0% was the correctly predicted based on the model. Now we can calculate sensitivity, specificity, positive predictive value and negative predictive value of the model. Before that, you need to make a table. How many of the predicted are really having heart disease? How many of those not predicted by heart disease by the model are really having heart disease? So we need to make a table format like this. And true positive. True positive means they are predicted as heart disease by model and actually they have heart disease also. False positive means they are predicted as having heart disease but actually they don't have heart disease. False negative means they are predicted as no heart disease but actually they have heart disease. And a true negative means they are predicted as not having heart disease and they actually don't have heart disease. So 10 people were true positive. That means they are predicted as having heart disease and they have heart disease. 6 people were false positive. That is, they are predicted as heart disease but they don't have heart disease. 25 people were false negative. That means they are predicted as not having heart disease but actually they were having heart disease. 59 people were true negative. True negative means they don't have heart disease and they are predicted as not having heart disease. So sensitivity is true positive divided by total diseased individual. So true positive divided by true positive plus false negative. That will give 0.2857. Specificity. True negative divided by total not diseased. True negative is 59 divided by total not diseased is 65. So 0.9077. So 90.77%. Sensitivity, when you convert into percentage, it will be 0.2857 multiplied by 100. So 28.57% is the sensitivity. Now we can calculate positive predictive value and negative predictive value of the model. Positive predictive value means true positive divided by true positive plus false positive. So in this case, it is 62.5%. Negative predictive value means true negative divided by true negative plus false negative. So we got 70.24%. Now we can look at the variables in the equation. This is the main result of logistic regression. Simple binomial logistic regression. Okay. For age, it is showing exponential b and a 95% confidence interval of exponential b. Exponential b is the odds ratio. Okay, as all of us know, if odds ratio is more than 1 and a 95% confidence interval of exponential b or odds ratio does not cross 1 or does not include 1, that independent variable is a significant risk factor. So here odds ratio is more than 1, 1.088, and 95% confidence interval of odds ratio is between 1.032 to 1.146. So both the lower limit and upper limit of 95% confidence interval of odds ratio are more than 1. So it is a statistically significant risk factor. We can cross check. Look at the significance value. It is 0.002. That is less than 0.05. So it is statistically significant. So how to interpret increasing age was associated with an increased odds of exhibiting heart disease. For each year increase in age, odds ratio to exhibit heart disease was 1.088. That means 95% confidence interval of odds ratio was from 1.032 to 1.146, and p-value was less than 0.01. So it is statistically significant. Now we can see how to present the result. A binomial logistic regression was performed to ascertain the effects of age on the likelihood that participants have heart disease. The logistic regression model of including age as the independent variable was statistically significant. Chi-square value was 11.907 and a p-value less than 0.05. The model explained 15.5% of the variance in development of heart disease and correctly classified 69% of cases. Sensitivity of the model was 28.57%, specificity was 90.77%, positive predictive value was 62.5%, and a negative predictive value was 70.24%. This is a way you have to present the result in your publication.